Hi, it's Professor Tierney. I wanted to take some time to make a video about creating Haworth structures from Fischer projections because I know there's a lot going on, and I'm sure a lot of people would appreciate the ability to pause my lecture in the middle of doing some examples. So I'm going to do two examples for you. These come from our class notes, and we are going to be doing A is alpha D galactose and B is beta D fructose. And I chose these two because one is an aldose. Our first galactose is an aldose, whereas fructose is a ketose, and they're very similar, but there's like one major key difference when you're treating these that I wanted to go over. So whenever you are creating a Haworth projection, a Haworth structure from a Fischer projection, the first thing that you have to do is you have to number the carbons top down. So let's do that. We're just going to do galactose for right now. So that's going to be one. Oh, I need to have a pen, don't I? Hang on just a second. Let me create my pen. Okay, so we have 1, 2, 3, 4, 5, 6. Okay, so we are doing that for reference for when we get to filling in everything once we draw a ring. Now, in order to draw a ring, we need to figure out how many points that ring is going to have. The key to this is knowing that every point, so every carbon in the ring is going to be a chiral carbon. So right now, the chiral carbons that we're starting off with are wherever we see an intersection. So we have 1, 2, 3, 4 chiral carbons. Our carbon that's in the carbonyl group, so the C double bond O, that will become chiral when we put it into the ring. So that will always be included in the ring. And this is going to become in the ring what is known as the anomeric carbon. And that one is important. So we have basically, you can take your number of chiral carbons and you can add 2 to it to figure out how many points are in your ring, because in the ring, we're going to have our 4 chiral carbons. Our aldehyde carbon will become the anomeric carbon, so that's going to be in there too. So the C double bond O, that becomes a single bond, it becomes chiral. And then oxygen will also join the ring. That oxygen comes from the carbon 5OH group. So if I have 4 chirals plus my anomeric carbon plus my oxygen, that's going to be 6 in this one. Shorthand, you can just count your chiral carbons and add 2, and that'll tell you how many points are in the ring. I kind of just figured that out while we were doing lecture the other day, so that's a nice shortcut. Count your chiral carbons, add 2, that's how many points you have. So when we have our points, we're not going to draw a cyclohexane because one of those points is going to be an oxygen. And it's always, if we're drawing a hexagon, it's always going to be in the upper right corner. All right, that's our oxygen. I'm just going to go ahead and draw all of my vertical lines at every carbon point. So now we have oxygen and 5 chiral carbons. I like to start from the backwards. I actually like to start from the bottom of my Fischer projection, because when we have a D monosaccharide, what happens is this CHO2 is always going to end up on the top of the carbon directly to the left or directly counterclockwise from the oxygen. So this O is the oxygen in the ring. CH2OH goes on top, and this is going to go on the bottom. So from our counting, we saw that this CH2OH, that's our 6 carbon, which means this is 5, 4, 3, 2, and 1. And that makes sense because when we count it down, we saw that carbon 1 was going to be our anomeric carbon. So the anomeric carbon is always the one that's directly to the right or clockwise from the oxygen in the ring. So now that we've got carbon 6 and 5 taken care of, let's look at our anomeric carbon. So our anomeric carbon, we are going to look at what isomer is asked in the question. You're either going to be asked for an alpha or a beta. Here we're asked for alpha, which means we're going to put an OH on the bottom. We're going to see when we're doing a beta, we put an OH on the top. Now, that OH, remember, that is actually coming from this O in our aldehyde. That became this OH. So the other thing that's coming off our carbon is this H, and that's going to go on top. Now we're going to fill out our carbons 2, 3, and 4 according to what the Fischer would look like if we tipped it over 90 degrees. So if I tipped my Fischer over 90 degrees, everything that's on the left is going to end up on top, and everything that's on the right is going to end up on the bottom. So if we're looking at carbon 2 with H on the left and OH on the right, that means that we're going to end up with H on top and OH on the bottom. For carbon 3, it has the opposite. OH on the left, H on the right means that OH ends up on top and H ends up on bottom. Oh, maybe for the next one, I should do a couple different colors for my pens. And then for carbon 4, we have OH on the left, so that ends up on the top. Sometimes you'll see OHs written as HOs if there's more space to write the H on the left. You can write it as OH, that's fine. And H ends up on the bottom, so that's carbon 4. So this would be our Haworth structure for alpha D galactose. Let's look at beta D fructose. So beta D fructose, we're going to start off the same way. So I'm going to actually change my color of pen for numbering to red. And we're going to number the same way we did, just top to bottom, 1, 2, 3, 4, 5, 6. All right. Now, once again, I'm going to take one more different color. I'm going to take advantage of all these colors. Okay, we're going to count how many points our ring is going to have. Remember, we can take our chiral carbons, 1, 2, 3, plus the carbon in the C double bond O, the carbonyl group, that's going to become chiral, and then the oxygen is going to join. So we had 3 chiral carbons to start. We add the carbonyl carbon and the oxygen. This is going to be a 5-sided ring. When we do a 5-sided ring, we typically put the O at the top. So I'm going to draw a pentagon with an O at the top. 1, 2, 3, 4. Okay. So here I'm going to do exactly what I did last time. I like to start with carbons 5 and 6 because those are pretty reliable. Whenever we have a D hexose, which is I'm only going to give for my class for problems, we'll just be doing aldohexoses and ketohexoses that are all of the D isomer. So we're going to see that the CH2OH, once again, it ends up on the top to the direct left of the O in the ring, just like we saw before. That's our carbon 6, and then the H ends up on the bottom. So now I can number the carbons in the ring. This is carbon 6. This is 5, 4, 3, and now our anomeric carbon is carbon 2. That does match what we have. So remember, the C double bond O for a ketose, that's not going to be carbon 1. That's going to be further down the chain, somewhere in the middle. So if we drew it right, the carbon that matches for the anomeric carbon, the one directly to the right of the O, should match the carbon that had the double bond O. And it does. So we did it right. Okay, I did it right. So let's take a look. I'm not going to worry about that just yet. I'm going to show you how we can draw in carbon 1. First, before we can draw in carbon 1, though, we have to draw in the oxygen, the OH group that makes this a beta isomer. So we are asked for beta D fructose. So beta means top. So our OH group is going to go on top. I know I want beta to be bottom too, but it's just the way it is. So our OH group on carbon 2, that's coming from this double bond O. Now, the other thing that's going to be coming off the bottom here, that is everything that's on top of your ketone. Okay, so that's going to be this CH2OH, the carbon 1. That's going to go on the bottom here. And that, if we were to then number it, which isn't necessary, but just so you can see where all 6 carbons are, that's our carbon 1. So we will have carbon 1 hanging off when you have a ketose. It's an H when it's an aldose. So now to fill out the rest of the remaining groups, we are going to pay attention. So when we go to the next carbon, notice this is carbon 3. I need to go back to my carbon 3 on my Fischer projection, and I see that OH is on the left and H is on the right. We tip it over. Everything that's on the left ends up on top. So the OH is going to end up on top, and the H ends up on the bottom. On carbon 4, it looks like we have the opposite. OH is on the right, so it will end up on the bottom, and the H was on the left, so it ends up on top. I hope these examples were helpful, and let me know if you ever have any other topics you'd like to see a video for. I'm happy to take a moment and do a couple examples that you can watch as many times as you want. Apparently, I don't know how to stop recording when I'm sharing. Anyways, good luck with your chemistry. Have fun studying.